Building on our previous lesson on solving linear simultaneous equations, we're now going to look at some more difficult ones involving quadratics. And importantly, we're going to look at how we use the discriminant from the quadratic formula, the b squared minus 4ac element, to inform us about the number of roots, whether we've got two distinct roots, one repeated root, or no real roots, and have a look at graphically what this means. So we'll start off with this fairly straightforward y equals x squared and the straight line graph 3 minus 2x. If we look at the graph, that's what it looks like. Probably could use a graph to read off the values, but it's not always convenient to draw one, and a lot of the time the graph won't be accurate enough. So we do need an algebraic method. But we can see clearly what's going on here. We have these 2 points of intersection. And when we're involving a quadratic, this is often the case. Okay, so there's the two equations. They're both y equals, so we can equate the right-hand sides like so. If we then rearrange to make a quadratic equal to 0, it's in the form ax squared plus bx plus c, isn't it? With the a as 1, the b as 2, and the c as minus 3. We can factorise this quadratic like so. X minus 1, x plus 3 equals 0, which from our null factors, making the either bracket 0, we get x equals 1 or x equals minus 3. And those are our two x values. To find the y values, we simply put them into either, because they work in both equations. Usually use the linear one, it's usually easier, but not always. And we end up with the points of intersection of 1, 1 and minus 3, 9. Sometimes it's necessary to rearrange the linear equation before we eliminate y. For example, in this one here where we haven't got two y equals, if we rearrange the linear equation to make it y equals, then we can apply the same approach as previously. Equate the right hand sides, rearrange to get our quadratic, factorises again, and we get two solutions for x, sub them in, usually again into the linear one, to find our y values. And there we are. Minus 1 minus 2 is 1 point, and the other point is 4, 13. Okay, have a go at this one yourselves. Pause the presentation and have a go. Okay, so you needed to rearrange the linear equation, then equate right-hand sides, organise your quadratic to make it equal 0, factorise, find your x solutions, and then sub them into the linear equation to find y. And we end up with those 2 points of intersection. Right, there's some quite important issues here about how many solutions that you get and how we can discover how many solutions we expect. Well, we can see from these graphs here that there's no points of intersection. There's the equations. This is of the blue straight line graph. This is the red quadratic curve, this parabola here. We can see they don't meet. So let's try and solve the equation simultaneously and see what happens. Well, we use the same approach, equating right-hand sides. If we try and solve this, we'll find there's no real solutions. If we look at the discriminant, the b squared minus 4ac part of the quadratic formula, we find that we get minus 3. And because that's negative, it's less than 0, that informs us that there's no real roots. So every time the discriminant is less than 0, the quadratic equation will have no real roots. Second example, same approach here. Here we find that the discriminant is equal to 0. And what that tells us is it has what we call equal or repeated roots. And if we factorise here, we can see that we've got x plus 2 squared, x plus 2 all squared. We've got it repeated. In other words, x minus 2 is a solution, and the only solution. And we can see what that means graphically. That means that the straight line is a tangent to the curve. To summarise, if we have a linear and a quadratic equation representing a line and a curve, we can solve them in the way that we've just done. And importantly, we can use the discriminant part of the quadratic formula when they're in this form here, ax squared plus bx plus c, to tell us how many points of intersection. If the discriminant's greater than 0, we have 2 points of intersection. If the discriminant is equal to 0, we have a repeated root. The lines are tangent to the curve. And if it's less than 0, then the line and the curve don't meet, and we have no real solutions. Okay, to finish off then, have a go at these three. Decide whether these pairs of lines and curves meet. If they do, find the points of intersection or point of intersection if it's a repeated root. And then have a go at sketching the curve and the line. Pause the presentation, have a go. If you're successful, then you're ready for the lesson. Okay, so the first one, same approach, reorganise, equate right hand sides. So reorganise this linear one, make it y equals, then equate the right hand sides. Get the quadratic in the form ax squared plus bx plus c equals 0. Look at the discriminant and it's equal to 0. So that tells us that the lines are tangent to the curve. We have one repeated root. We then factorise. We can see that is the case. X minus 1 is a solution. That gives us a y value of 4 if we put it into here. And we can see here what the sketch looks like. Okay, the next one, these are already y equals, so we can just immediately equate right hand sides, organise the quadratic into the form we need it, and the discriminant has a value of 9, so that suggests we've got 2 points of intersection because it's positive. And if we factorise, we can see that is the case. And x equals 2 and x equals 5. Work out the corresponding y values by subbing into the linear equation here. And that's what it looks like. We have solutions at 2, 7 and at 5, 28. And the final one, rearrange the linear one, equate right hand sides, arrange the quadratic into the form with the ax squared plus bx plus c equals 0. Check your discriminant. This time it's negative, which suggests that there's no points of intersection. And we can see from the sketch there that that's the case. The line and the curve don't meet.